Okay, welcome to your next lesson, mass, weight, and density. So this lesson is about, well, obviously those quantities. These are some physical quantities that we will need to be able to calculate with, measure, and use in physics. So we're going to start with this. We're going to start by defining mass and weight, which are different things, and it's really important that you understand the difference between mass on the one hand and weight, which is something different. Okay? So here we go. Here's a definition of one of those terms. I wonder if you can guess which one it is. I'm going to write it down here. How much stuff, it's not a super technical definition, but how much stuff is in an object? Have you guessed it? It's the mass. The mass of the object is how much stuff is in it. So I guess that makes the next one pretty easy here. A measure of how hard gravity pulls an object. That is, of course, weight. Weight. Alright, so mass versus weight. They are different things. Mass is just sort of a measure of how much stuff there is there. How much stuff. I mean, it's not a technical definition, but it's one of the best ones I can come up with to help you understand the concept. Weight, however, is a force. So weight has different units from mass. Mass is measured in kilograms. All right. Weight is measured in a unit that's called newtons. Newtons, named after Isaac Newton. It's abbreviated with a capital N. So when you talk about how much you weigh, technically you should be using the term newtons, not kilograms, which is counterintuitive because I know that everybody, when they're talking just to people, how much do you weigh, you might answer in kilograms, or you might answer in pounds if you're from the US. Anyhow, kilograms is not actually a measure of weight, it's a measure of mass. Now, just looking at this image down here at the bottom, you can see here's a pile of feathers right here, and then over here we have a pile of bricks. Now the thing they're on is balanced, so what do you think that means? It means they have the same weight, and in fact they also have the same mass. Right? But you can see that the feathers take up a lot less space, or a lot more space rather, than the bricks because the feathers are less dense. Now that leads us into our next topic. But before we move on and talk about density, which is our next topic, we'll go ahead and talk really quick about an alternative definition of mass, and that is basically a measure of how difficult it is to change an object's motion, or easy. So if you've ever played wiffle ball, here's a wiffle ball. They're very light, they're made of plastic, you can throw them very easily, and you can stop them very easily. You can hardly tell the difference if it hits you. So, very easy, very low mass. It's extremely easy to stop it if it's moving, and it's extremely easy to start it moving if it's stopped. Now let's contrast that with a bus. Obviously a bus has way more mass than a wiffle ball. How can you know that? With this definition, basically if a bus is moving, say 50 kilometers per hour down the road, and you try to stop it with your body, that's a bad idea, not going to work, right? A bus is really hard to stop when it's moving. It's also really hard to move when it's stopped. If you try to push a bus, even if the brakes are off, if you try to push it with your bare hands or pull it with your legs, you're not going to be able to, probably, unless you're a really strong guy who does that for competitions. You know, it's really hard to move a bus because it has so much mass. So anyway, that's an alternative way of thinking about it. The more mass something has, the harder it is to change its motion. If it's stopped, it's hard to get it moving. If it's moving, it's hard to make it stop if it has a lot of mass. Here we have density. So what is density? Density is basically a measure of the mass of an object divided by its volume. So you've got mass and you divide by volume. So we were just talking about what mass is. Volume is just basically how much space a thing occupies, how much how much space it occupies. So let's take an example. All right, aluminum. Here we have an aluminum can. Here we have an aluminum airplane. Airplanes are not all aluminum, but the main body of the airplane is generally made out of aluminum. All right. No matter what kind of aluminum we have, no matter what shape it's taken, what it's being used for, aluminum all has this density right here, 2.7 grams per cubic centimeter. It's a property of aluminum that is its density. So how could you find that out? Well, we could, we'll talk about that in just a minute. Actually, that's our next slide. So to find the density of an object, basically you need to know its mass. Generally you'll use, in class, we'll use balance, an electronic balance to find mass. Sometimes we might use a little bit of a different device to find the mass if it's really heavy. All right, and then you have two ways to find volume. One way is basically by displacement. If it's an oddly shaped object, like a rock, or some kind of other object that does not have a clear shape, sort of bumpy, lumpy, odd holes in it, stuff like that, then you need to use displacement to find the volume. And basically what you're going to do is you take a certain volume of water here, you stick the object into that water, and you see how much the volume changes from here to here. The change in volume is equal to the volume of the object. All right. So the other way you can do this, if it's a very clearly defined shape, like a cube or a cylinder or a rectangular solid or something like that, such as what we have here, then you can basically calculate the volume using your volume formulas from math. So in this case, it would be height times length times width, depth in this case. All right. So basically, just multiply those three together, you would get the volume. And then once you have both of those quantities, once you have mass and volume, then you just divide mass divided by volume. That gives you the density. All right, and then just a couple of sample problems really quick. We have here an example problem of finding the density of a piece of metal. And as you can see there, the piece of metal is a regular shape, so we would use method number 2 from the previous diagram, or slide, and that would give us 5 times 10 times 2, so let's do that really quick. Multiply those together, those guys right there, and we would get 100 cubic centimeters. All right, and then we know that the mass is 250 grams, so 250 divided by 100, very readily, you can tell that's going to be 2.5 grams per cubic centimeter. All right, so that's an example of calculating density. Now if we look at this next problem, it's a problem involving mass and weight. So this table shows the weight of a 10 kilogram mass on 5 different planets. They're measuring in newtons, 10 kilogram mass. Mass never changes regardless. You can have the same mass on Earth as you have on the Moon, as you have on Mars or Venus, but your weight is going to change because weight is a measure of the pull of gravity. Gravity is different on each of these planets from Earth. So this tells you how much the 10 kilogram mass would weigh on each of those planets, and you can tell it's different for each one. Now, the question becomes, which planets would an astronaut have a smaller weight than on Earth? And all you have to do is look there at the list. So which planets have a smaller weight than on Earth? And here Earth is 100 newtons for this mass. Venus is less than that, Mercury is less than that, and Mars is less than that, but Jupiter is more than that. So the answer would be Mercury, Mars, and Venus, and that is going to be this one. Okay, hope that is clear, and we'll work more with this in class.